Hey everyone, nice to see you again. Today we're going to look at tensor computations using tensor add-ons. This will be the video blog entry for the post tensor computations using tensor add-ons. We'll go ahead and get to the cut screen, the logo screen, and I'll say a little bit more about what's going on. So in this video, we're going to kind of expand on the Maple Conference talk, Maple Conference 2022 talk. There I had about 12 minutes to talk about things. So in this video, we're going to be a little bit more leisurely about it. So let's go ahead and get into the post over here. Okay. I think first things first, let's kind of realize that my script was pushed ahead a little bit because of the conference. I had to talk about some pretty technical stuff. I had to talk about tensors. And so I just want to say that in the very near future, I'm going to be doing some more accessible things about tensors, talking about matrices as storage, drawers, like you put things in drawers, or you have shelves on a wall that you store things on. So it's possible to think of tensors as storage mechanisms. And I have a lot to say and have written quite a bit about tensors. And we're going to, in the near future, put some posts up that talk about tensors, first matrices and vectors as storage. So we'll do that in the very near future. But in the meantime, I wanted to go ahead and get into tensors, as we're seeing on the screen, and the idea is that what a person would do on paper. You can see some paper computations happening here. What one would do on paper, I would like to and have tried to mimic that in the tensor add-ons package in Maple. So we can see some matrices appearing on the left, and I'm trying to create the same sort of code and the same sort of notation on the right that one would write on paper. And then once you have these tensors created with their different symmetries, the first matrix has no symmetries, the second matrix is anti-symmetric. Once you have those tensors created, you can multiply them and then get a description of those tensors in the code. So, at some point, we're going to meet at the end and see what the answer to two matrices multiplied by each other is going to be. So we're about to converge here. Here's the output of this code, and I know there's a lot going on. So, if you want to see more about what's going on, read the post or watch this video over slowly, and you can pause it. But we can see here that the output of the code is the same as what you would get from handwriting. Okay, so this is the goal in general. Okay, the key to tensors and tensor computations is thinking of them as multidimensional storage. Here I've got a matrix, some medical data, patient height and weight data. We're going to give this tensor a name as you would on paper. You can see a view of it over here, the names, heights, and weights. And you can also, with tensors, create multiple views of that data, and just depends on what sort of information you want from it. So how are you going to slice that data? Okay. The key to tensors is dealing with their multiplication. When you talk about multiplying tensors, we're talking about transvection by contraction. And here we have a variety of tensors of different ranks, different dimensions and sizes, different dimensions, let's say, and then we can multiply them, see their data all mapped out, and then multiply a tensor A times B times V times W. And here is the result at the end of the day. So behind tensor add-ons is a way to visually see the shape of the tensors you're multiplying and to correctly do the multiplications. Okay. Beyond just the multiplications, we want to make sure that, you want to make sure that these tensor computations aren't just done in isolation. There is a reason we're doing these computations, and I will let you read about and I will illustrate in a moment the philosophy that I'm talking about here. But let me reload this page. So here we can see, sorry, we could almost see, there we go, some output from our computation. It's nicely summarized. It's kind of complicated to look at, but you can see here that one of these computations is this matrix. And my philosophy is that any matrix should be accessible, and then possibly you can pass that matrix to another application and then do some solving of equations and some plotting and perhaps that other application. And here you can see the solutions, a bunch of data. You can create some visual plots of it. And very importantly, we can see here that we did our computations correctly, because this plot here shows that the angle between some vectors is a constant, and that other plot shows that the vectors are the same length. I mean, what we're going to see here is some pretty pictures come up next, but I want to point out that first and foremost, like, we had to do the computations here in Maple correct first. I mean, if you don't get the computations right, then pretty pictures aren't going to matter a bit, because it's possible to create pretty pictures that are not correct. So we really want to, the advantage of Maple and the tensorAddOns package is that it allows us to do these high dimensional computations correctly. Okay, so I want to look at an example. The main example we're going to look at in this video is the comparison of computing the Riemann curvature tensor using the tensor package, tensorAddOns, and the physics package. What you're seeing here as a precursor to that is computing the Gauss curvature. And Gauss curvature, we can see, is just a ratio. Compute the area of that pink region and the area of this region on the sphere, and look at their ratio. And as the regions get smaller and smaller, that ratio in the limit is this quantity called the Gauss curvature. So Gauss curvature is just a ratio of areas. We've, in a previous post and also on Apple Books, written in an animated graphic novel format, we've written about the Gauss curvature and some of the ideas, mathematical ideas behind that. So if you're interested, by all means, please check out A Curvature Story on Apple Books, right? But in the meantime, right, we like to look at the tensorAddOns package and what it has to say about Gauss curvature. And we're going to get to Gauss curvature by going through the Riemann curvature on a surface. And here again is our philosophy illustrated, that when you run a command in the tensorAddOns package, that there's essentially two parts to that. There is the output summary, this part here that shows some sort of summary that I've chosen to show. And then there is also an accessible part, an accessible data part that is up, that the user can access and then do a variety of other computations with, right? And create their own output summary. So here we can see that some of the accessible data from the Riemann curvature on a surface is the Riemann curvature tensor, right? And the Riemann curvature tensor has this symmetry. You'll notice that as a large matrix, it's anti-symmetric, but each of the individual matrices is not anti-symmetric. Here is this matrix, it's not anti-symmetric, or else it would have zeros on the diagonal. But there is a concept of the lowered curvature tensor, which is also some of the accessible data. And if we access that, we can, and show it, we can see that it does have the symmetries, that is an anti-symmetric matrix of anti-symmetric matrices, right? And one can then take that lowered curvature tensor and kind of do a mixture of the differential geometry and the physics package to kind of do the differential geometry for the higher derivative computations. And then one can show that computation in a basis, which is more of a differential geometry idea. And we can do that to create the curvature two forms in tensor in the tensor basis, or we can create the curvature two forms, in the wedge basis. So that's what we're seeing here, an antisymmetric matrix of two forms. And the fact that we got that symmetry structure leads us in the direction that we feel like we got the right curvature computation correct. Kind of know we're in the right direction too if we run surface data. Again, we're seeing an output summary, and that output summary shows us the Gauss curvature here in the lower right is actually a formula that is the 1, 2, 1, 2 entry of the curvature tensor divided by the determinant of the metric tensor. Again, this is encoding the ratio of areas that we saw earlier, and that's what the Gauss curvature is. So tensorAddOns, we're seeing that philosophy again, that there is an output summary, and then from that summary, there's also data that can be accessed by the user to do computations or see computations that are maybe not in the summary. For example, maybe the curvature two forms can be accessed from the data. And here we're seeing that data showed to us as a 2 down tensor, a -1, -1 tensor. Okay, so the goal of the rest of this talk is to do the curvature tensor for the Schwarzschild metric, but just to kind of set the idea of what we're trying to do, here is a tensor created from tensorAddOns package. We've created a general tensor that's antisymmetric in the first and second and the third and fourth entries. So we're seeing an antisymmetric matrix of antisymmetric matrices. So really there are 36 entries that we need to fill in the upper triangular part of all the upper triangular parts of this matrix. And so computing those 36 quantities is what we're going to see in the tensorAddOns package and the physics package compared. Okay. Okay, not getting in, well, maybe we'll see what sort of detail we get into, but I do want to set the stage again that tensorAddOns is built off of the tensor package. It's increased functionality from the tensor package with still some of the similar data type under the hood, but with some added functionality that allows the user to use atomic variables to name their tensors as would be done on paper. Okay, so what we're seeing here is when one does computations with tensors, a good idea maybe to start by setting up a frame. Here we're going to set up a frame for the Schwarzschild metric. We're going to access some of this data, and we can see some of that data shown to us below. All right, we've seen the metric tensor and we're seeing the frame itself. Okay, that data, the metric tensor, becomes an input to this function called the connection coefficients, and the connection coefficients are output as a summary in pink here. These connection coefficients are a precursor to the Riemann curvature. The connection coefficients are a rank 3 tensor, and we can see that there are multiple ways to view that tensor, 3 different permutations of it. I've isolated the second permutation, the one that shows that the rank 3 tensor can be viewed as a vector of matrices, and each of those matrices is symmetric. You can see that the numbers are same on the diagonal as on the upper triangular is the lower triangular part. So that's a known result that we know about the connection coefficients, and so that view shows us something nice and visual that's a result we expected to see. Okay, the physics package will set up their frame by this call to G, I guess, which sets up the Schwarzschild metric in that particular frame, and then does the computes the Christoffel symbols via this formula. Right here I've written how that might appear in tensor notation. really we're creating the Christoffel symbols of the second kind. That's what the physics package is doing, and creates a Christoffel symbols which can be viewed as an array. And we don't see the whole array when you first output summary this thing. You're seeing a slice of it. It's hard to tell which slice, but if you show all the slices and then put those slices together as a vector of matrices, we can see that these compare to the tensorAddOns package. So this idea of showing all the slices and then putting them together into a matrix of vectors or a matrix of matrices is what the matrix view command is doing. So there we have it. An added feature of tensorAddOns is that any sort of output that can be accessed, the reason you're accessing it is so that you can do something more with that data. For example, we might take the connection coefficients and compute the connection one forms from them, and that's what we're seeing done here. So we're seeing, yeah, there we have it. Okay. I do want to point out something that I do worry a little bit about the physics package is that from the literature, the connection coefficients are essentially like the Christoffel symbols of the second kind, but there's also some additional terms, at least, possibly one other equation that the tensorAddOns package does account for. And the reason why the physics package and the tensorAddOns package compute the same answer is because in this Schwarzschild metric example, there is some additional terms. The second equation is a vector of all zero matrices. So effectively, we get the anholonomic terms, these extra terms that comprise equation 2 are all zero. And that's why our answers are coming out to be the same with the physics package. Okay. The Riemann curvature in tensorAddOns accounts for these anholonomic terms, but in this example, they're all going to be zero. And here is the Riemann curvature for the Schwarzschild metric. A better view of that is kind of hard to, you can see that it's an antisymmetric matrix. Well, antisymmetric matrix, but each matrix is not necessarily itself antisymmetric. If you look at, you can see here that when you go to the curvature two forms, it's an antisymmetric matrix of two forms, which is a known result that we expected. So the curvature two forms can be created from the accessible data. Okay. I do want to point out that with the physics package, we can see here that there's no additional anholonomic terms on the end, right? So that might be some functionality that tensorAddOns has that physics does not. And we can see here that when you compute the curvature tensor with the physics package, you do get a slice of the output is a slice, some slice, I don't know which one. And if you want to list out all the slices, I'm not sure which ones these are, and there are more slices, and then how would you kind of put them all together? And at that point, you might as well just use the tensorAddOns package, okay? So I will leave you all to read this, but I do wanted to, for those that are interested in some of the background behind the tensorAddOns, there is some discussion about the tensor data type in Maple and how the tensorAddOns kind of added to the functionality of that data type, particularly when it comes to the symmetries and of the tensor and showing description of the tensor and a particular viewing tensor. So this is kind of what we've added to. Okay, I don't want to spend a lot of time here. It's probably better read. Okay, but I do want to point out with the other example that tensorAddOns it might be able to handle examples that the physics package cannot. For example, from the literature, Fred Ackerlin has written about some of the Schwarzschild metric in an orthonormal frame. and done the computations by hand. So to double check the tensorAddOns code, here we have all the computations. We can see here that tensorAddOns allows for the connection coefficients and the curvature to include anholonomic terms, these terms involving the letter C. So we can see here that this term is not all zero. So we're in an anholonomic frame. And here we have the connection 1 forms matching the literature that was done. Okay, the Riemann curvature, we can see here we have in this case it's an an antisymmetric matrix of antisymmetric matrices, I believe. And here are the curvature 2 forms and the Ricci curvature and that kind of stuff, which matches with the literature. So the ability of tensorAddOns to handle the anholonomic frames and different views of the tensor, and gives users a lot of functionality when it comes to summarizing a lot of tensor computations and giving users access to that data for further use is a key feature of the tensorAddOns package. Okay, if you'd like to read more, I think reading would really help get into some of the technical details, but you can check out unconcise-math.com. You can see some more about the functionality of the tensorAddOns package. We have 36 functions at this point, and many documentation examples that need to be written about and tested. If you'd like to see more, unconcise-math.com. You might also check out the short version of this video for the Maple Conference 2022. And of course, you can always check out the unconcise-math.com, the posts themselves that refer to Maple Conference 2022 and the tensorAddOns package. Thank you all for your attention, and I hope you found this helpful, and we'll see you all later for hopefully some posts that deal with a more accessible and introductory look at tensors and that kind of thing. So I guess we'll see you all later. Thank you for your attention, and I appreciate you.